Hello everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and discuss what it means for a function to be differentiable. So, we're going to begin as usual with a closed and bounded interval, a to b, and let's assume that f maps that closed and bounded interval to the set of real numbers, and let alpha be a point in that domain. Then we say that L, a real number, is the derivative of f at alpha if, for all epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and alpha is made to be arbitrarily small, then the distance between this function here, which I'm just going to call g of x temporarily, and this number L is arbitrarily small as well. So if you look at this, practically this is just the definition of the limit as x approaches alpha of g of x being equal to L, right? So that's practically all a derivative is. A derivative is just a limit. So if L exists, then we say that f is differentiable at that point alpha, and we're going to write that f prime of alpha is equal to L. Also, if f is differentiable at all points in its domain, then we say that f is differentiable on its domain and write that f belongs to the set of differentiable functions on that domain. So, from this observation that this is practically just a limit, we can actually give an alternative and equivalent definition of a derivative. In particular, the derivative at a is practically just the limit as x approaches alpha of f of x minus f of alpha all over x minus alpha. Right? So that's all a derivative is, provided that this limit even exists. The first theorem that I want to present about differentiable functions is the following. Let's assume that f maps a to r, and let's assume that f is differentiable on a. Then, if this is true, then f is also continuous on a. If you want to try this proof on your own, I recommend pausing this video and trying it, because the proof actually is not super difficult. So we're going to, let's assume that x belongs to a, and let's assume that a belongs to a as well, with x and a not equal to one another. And then what I want to do is I want to consider the limit as x approaches a of f of x minus f of a. Because if f is continuous at a, then this difference should be equal to 0. Because the limit as x approaches a of f of x should be equal to f of a if f is continuous there, right? But we can't assume that. So what is this going to be? So this is going to be equal to the limit as x approaches a of f of x minus f of a, and since we're given that this function is differentiable on a, I need to introduce the difference between my domain values x and a. So I'm going to have x minus a there and x minus a there. So I'm just multiplying top and bottom by 1. From here I'm going to use the properties of limits, in particular the limit as x approaches a of f of x minus f of a all over x minus a, and then I'm going to multiply by the limit of that second function, so the limit as x approaches a of x minus a. Keep in mind x minus a is just a function, so as x approaches a, the limit of that function is equal to the function evaluate that limit because all polynomials are continuous, and this character right here is just the derivative of f at a. So that means this is going to be equal to f prime of a times 0, which is going to be equal to 0 regardless of what the derivative of f at a is equal to. So we have that the limit as x approaches a of f of x minus f of a is just equal to 0, which means that the limit as x approaches a of f of x is equal to f of a. So that means that f is also continuous on a, and that completes the proof. So a very important connection with this also is the following. So if we have a function being differentiable on that domain, we've proven that f is also continuous on that domain. And you should also note that if f is continuous on the domain, that means f is also Riemann integrable on that domain as well. Right? Keep in mind that Riemann integrability does not necessarily imply continuity, and continuity need not imply differentiability. So you should be able to come up with a few counterexamples for both of those statements. The next theorem for derivatives gives us your basic rules that you typically encounter in a typical first semester calculus course. And it says the following. Let's assume that f and g are both differentiable functions on some domain A, and let's assume that c is just a constant. Then any scalar multiple of a function will also be a differentiable function. Now, Just because it's differentiable doesn't necessarily mean you know what its derivative is, but the scalar multiple rule says that the derivative of the scalar multiple is actually equal to the product of that scalar with the derivative of that function. Also, if you have two differentiable functions and you add them together, then their sum will also be a differentiable function, and it says that the sum, or the derivative of the sum, will be equal to the sum of the derivatives. And from those two things, you can actually find that differentiation is a linear operator on differentiable functions. Moreover, if you have two differentiable functions and you multiply them together, then their product will also be a differentiable function. And we actually have a nice rule for finding the derivative of the product, and some people call this the product rule. And keep in mind, it's very important to note that the derivative of the product is not necessarily equal to the product of derivatives. Nice example actually investigates which functions actually satisfy that rule. But for all differentiable functions f and g, it's going to be equal to f prime g plus fg prime. Also, if you have two differentiable functions and you divide them, their quotient will also be differentiable as long as the bottom is not equal to 0 on that domain. And the quotient derivative, sometimes called the quotient rule, is equal to f prime g minus fg prime all over g, the quantity squared. Right? The last rule, some people call the chain rule, says the following: if f and g are both differentiable and you compose one with the other, then their composition will also be differentiable, and the derivative of the composition will be equal to the composition of the derivative of f with g multiplied by the derivative of g. Right? And some people call that the chain rule. So the proofs of these theorems are actually straightforward, and I will only provide you with the derivative of the chain rule because that's maybe the more interesting one. So what is the derivative of the composition? So the derivative of the composition at some point A in some domain A is equal to, at least by definition, the limit as x approaches A of f of g of x, that's the composition of f with g, minus f of g of A, all over x minus a. So that's just the derivative of a function. Now what I'm going to do is I'm going to multiply top and bottom by a special form of 1, and let's assume that g of x does not equal to g of a for all x in some neighborhood of size delta around a. If this is the case, then what we have here is this is the limit as x approaches a of f of g of x minus f of g of a over, so there's the top of our derivative formula, and the bottom I'm going to put over here. I'm going to put our bottom over there, and I'm going to introduce our special choice of 1. So our special choice of 1 is going to be equal to g of x minus g of a, and g of x minus g of a. So over here, if you notice that g of x is a variable and g of a is a variable too. So this is just the derivative of f with respect to that variable. So this is just going to be equal to f prime of that variable, which is just going to be g of a. And then over here, we're going to have, well, that's just the definition of g prime of a. So that's going to be g prime of a, and that is the proof of the quotient rule. Now, the chain rule. So there are several different notations that are often used for derivatives, and I just want to mention a couple of them. Some people will write f prime as d of f, so the derivative of f, and some people will also denote the variable that you're differentiating, quote unquote, with respect to. So this notation is practically on the operator perspective, in particular the linear operator perspective of differentiation. And then there's another family of notation. So some people will also view the derivative d over dx of f of x also as an operator, but it's focusing on a particular element x in the domain of f, right? So it's not really focusing on the operator perspective, but more so on the function image perspective. And some people will write derivative d over dx of f of x to represent f prime of x, so the derivative of f at x. And some people will even connect this with an equivalent notation of d of f of x. So this d is practically that notation just with respect to a different notation. And some people will say that this is equivalent to writing f prime of x times dx. Right, so this is another family of notation, and this is more targeted at the function image perspective of derivatives, right? Now, there are a couple things to be said about this later notation. In particular, notice I'm multiplying by dx. So what exactly does dx even mean in this context? And if that is the case, what does d mean in this context? Obviously, d would be an operator, and that's giving us a particular function times something. Right? So that usually is referred to as non-standard analysis or infinitesimal calculus, which we'll come back to at a later time, but I just want to keep this in the back of your mind because sometimes this notation is used interchangeably for a variety of reasons. The first application that I want to introduce for differentiation is that to limits. And this theorem is due to, or sometimes named after, L'Hopital. And it says the following. Suppose that f and g are both differentiable functions on some domain A, and let's assume that A belongs to that domain, with the additional property that f of A and g of A are both equal to 0. So if f of A and g of A are both equal to 0, keep in mind f and g are differentiable, which means they're continuous at that point. Which means if we see this limit, we're tempted to just plug that value of A into f and g. But notice that's going to give you this 0 over 0 thing. So you're like, okay, well, what can I do here? Well, L'Hopital's rule says that the limit as x approaches a of the quotient of f and g is actually equal to the limit as x approaches a of the quotient of the derivatives at the same exact point. Right? So it's a completely different function, f over g and f prime over g prime. They're completely different functions, but they have the same exact limit as x approaches a. And the proof of that is practically just a fancy or clever substitution. So let's do a quick example of L'Hopital's rule. And let's assume that we have the limit as x approaches infinity of e to the x plus x over the hyperbolic sine of x. So what is this limit equal to each other? Well, you're like, okay, well, e to the x plus x, that goes to infinity as x gets big, and so does hyperbolic sine. So this goes to infinity over infinity, where infinity is, say, an extended real number. But that's not what L'Hopital's rule says. It says, the top and bottom have to be equal to 0. But keep in mind, I can reciprocate this. For example, I can reciprocate the bottom infinity to the top, and I can reciprocate the top infinity to the bottom. And we know that if infinity is an extended real number, then 1 divided by that is going to give us some number arbitrarily close to 0. So infinity over infinity and then 0 over 0 are practically the same from the perspective of L'Hopital. So if you have an infinity over infinity form for that evaluation, you can still use L'Hopital's rule on that quotient. That means that this is going to be equal to the limit as x approaches infinity of the derivative of the top divided by the derivative of the bottom. So the derivative of the top, that's just going to be a basic sum rule for derivatives. So derivative of e to the x, that's going to be e to the x, and derivative of x is just going to be equal to 1. And the derivative of hyperbolic sine, as we already know, is just going to be the hyperbolic cosine function. And then we have this. But as you already know, e to the x plus 1 and also hyperbolic cosine of x are also going to go to infinity. So we can apply L'Hopital's rule again to this particular limit. So this is going to be L'Hopital's rule again because we have infinity over infinity, and that's going to give us what? So that's going to be equal to the limit as x approaches infinity of, so the derivative of e to the x plus 1 is just going to be equal to e to the x plus, because the derivative of 1 is just 0, and the derivative of the bottom is just hyperbolic sine of x. Again, we can repeat this process, but notice that the derivative of e to the x is just going to go to e to the x infinitely many times over and over, and hyperbolic sine of x is just going to switch to hyperbolic cosine of x. So applying L'Hopital's rule again is not really going to get us anywhere from here on. So the rest I'm going to leave for algebra. So what I'm going to do is I'm going to multiply top and bottom of this expression by the exponential e to the minus x, but I'm going to first rewrite hyperbolic sine of x in terms of its exponential form. Because remember that the hyperbolic sine of x is just equal to 1/2 of e to the x minus e to the minus x. So once I make that substitution, this is just going to be equal to 2, so the 2 from the 1/2, and then times the limit as x approaches infinity of e to the x over e to the x minus e to the minus x. And now I'm going to multiply top and bottom by e to the minus x. So once I do that, I'm going to have 2 times the limit as x approaches infinity of 1 over 1 minus e to the minus 2x. And we already know that e to the minus 2x is an exponential decay function, so that's going to go to 0. So this is just going to be equal to 2 times 1, which is going to be equal to 2, which is the limit as x approaches infinity of e to the x plus x over the hyperbolic sign of x. Right? So derivatives can come in handy when evaluating limits if that function is not that nice to deal with. The next theorem that I want to introduce is also related to limits, but it's limits of sequences. So let's assume that n is a natural number, and let's assume we have the sequence an, which is equal to n factorial all over the square root of 2 pi n times n over e to the power of n. Then this theorem, which is sometimes called Stirling's theorem, so this is due to Stirling, and it says that the limit of this sequence, am, is equal to 1. And the proof of this can be done, I'm not going to say easily done because I don't think it's super trivial, but it's due to creating some bounds for some definite integrals. So let's see if we can actually use this to our advantage to establish a limit of a very important sequence. So let's look at the sequence. Let's look at the limit of the sequence n factorial over n to the power of m. So keep in mind, this is not the limit as n goes to infinity of functions of real variables, because n is strictly set to be in the set of naturals, because that's what n factorial is defined on, right? So we're just going to be using this in a practical similar way and see what we get. So this is going to be equal to what? So by using Stirling's formula, keep in mind this is technically as n goes to infinity, so we can use this particular result. So that means n factorial and this object on the bottom are practically equal as n gets large. So that means this is going to be equal to the limit as n goes to infinity of the square root of 2 pi n. So the square root of 2 pi n, square root of 2 pi n, times n over e to the power of n, and we have that n over n at the bottom. So what are we going to do here? So the first thing I'm going to do is I'm going to rearrange this n over e to the power of n, and I'm also going to factor out that 2 pi square root outside of my limit. So I'm going to have the square root of 2 pi multiplied by the limit as n goes to infinity. On the top, I'm going to have the square root of n. I'm also going to have an n to the n. That e to the n is going to go on the bottom, and I'm going to have that n to the n that was already on the bottom. And do notice that n to the n are going to eliminate each other. And I'm just going to be left with the square root of 2 pi times the limit as n goes to infinity of the square root of n over e to the n. Now keep in mind, if it's true for the real number continuous form, then it's also going to be true for the sequential form, right? So if the continuation is decreasing, then any subsequence of it will also be decreasing as well. So we're going to extend this to the set of real numbers. In particular, we're going to extend this to 0 to infinity, because we know that the square root of n is defined on that interval for all real numbers n in that interval. And we're going to see what that's going to be equal to. So this is going to be equal to the square root of 2 pi times the limit as x approaches infinity of the square root of x over e to the x. And now we're going to use the differentiation principles. So square root of x is monotonically increasing, so is e to the x. So L'Hopital's rule definitely applies here. So it's going to be equal to the square root of 2 pi. So what is the derivative of the square root of x? Well, we know that that's going to be equal to 1 over 2 square roots of x, and the derivative of e to the x is just e to the x. And we can rewrite this to be a little bit more trivial, to be square root of 2 pi times the limit as x goes to infinity of 1 over 2 square root of pi, or that's the square root of x, and then e to the x. But notice the top stays 1 and the bottom grows without bound, so that means this limit is equal to 0, which means the entire thing is equal to 0. So that means the limit as n goes to infinity of n factorial over n to the m is equal to 0, which means that as n gets big, which grows faster, factorials or tetrations, and this says that tetrations will grow arbitrarily faster compared to factorial relations. The next few theorems that I'm going to present are very useful for optimization problems. The first theorem, sometimes referred to as the mean value theorem for derivatives, states the following. Let's assume that f is continuous on the closed interval ab and also differentiable on the open interval ab. If these things are met, then there always exists some number strictly between a and b, let's call it c, such that f prime of c is equal to fb minus fa over b minus a. And some people will refer to this as the average rate of change of f on the interval a, b, right? So there always exists a point c in between a and b such that the derivative and the average rate of change is equal to one another. Let's draw a little picture to sort of illustrate this very important idea, and this is very important for approximations. So let's assume that this point right here is A, and let's assume that this point right here is B. So if we connect these points with a line, then that line is going to have a slope, which some people refer to as the average rate of change of that function on that interval AB. So this theorem, the mean value theorem, states that there exists a point between a and b such that the derivative of the point equals that slope. And if we sort of look at this graph, it's probably this point somewhere here. Then the derivative of that curve at that point, which is the slope of the tangent line of the curve at that point, is approximately equal to or exactly equal to that average rate of change. So that's the point C. A corollary of the mean value theorem, for example, if we let f of a and f of b equals to 0, then the numerator of this is just going to give us 0 divided by b minus a to be equal to 0. So it states that if f of a and f of b are both equal to 0, then there exists a point c strictly between a and b such that f prime of c is equal to 0. So it's a direct consequence of the mean value theorem. So again, let's draw a little picture to sort of illustrate this. So we're going to assume that a is here and b is here and f of b are both equal to 0, then there exists some point c in between a and b such that the derivative is equal to 0, right? That is, the tangent line is a horizontal tangent line. Now, the next couple of theorems also are quite useful because keep in mind, if the horizontal line is tangent, then it is a potential local max or a potential local min. So theorem 7 actually gives us a more stronger version of Rolle's theorem, and it says the following. So let's suppose that f is differentiable on some domain D, and let's assume that a and b are any points in that domain, and let's assume that the derivative of f at a times the derivative of f at b is negative, implying that they are opposite signs. Then there exists some point c strictly between those numbers a and b such that f prime of c is equal to 0. So here, f of a and f of b need not be 0 as long as they have opposite signed derivatives, then the existence of such as z exist. So let's look at a little picture to sort of get an idea of what's going on here. So let's assume that we have this type of picture. And let's assume that we pick this point here. Notice that the derivative at this point is positive. And if I pick this point right here, the derivative will be negative. That means there exists a point C in between these points such that the derivative is equal to 0. Similarly speaking, I can choose another point over here, for example, D. Notice that it goes from negative derivative at B up to positive derivative at D, which means there exists another point in between B and D, let's call this point E, such that the derivative is equal to 0 between those points as well. Right? And that's actually very, very useful as well. So the next theorem in sequence is to figure out, okay, well, with this information, how can we directly tell easily that it is indeed a local max or a local minimum, right? Now, there are a couple variations of this, but the next one is a little bit more direct, at least in my opinion. But at least from this graph, you can see if the derivative switches from positive to negative, then it's definitely a local max. If it switches from negative to positive derivative, then it's a local min. But if you don't want to check at 2 points for 1 point, you can actually calculate the first and second derivative at the same exact point in order to get the same exact conclusion, but it requires your second derivative to be continuous. And this is called the second derivative test, and it says the following. So let's suppose that the second derivative is continuous on that domain A, and let's assume that A belongs to A. So only one point is required for analysis. Then, if the following is true, then we can guarantee that it's a local min or a local max at that point. So the first variation for this is the following. So if f prime of A is equal to 0 and f double prime of A is negative, and the second derivative is practically the same thing except it looks at the positive side, then f attains a local max at A, and if the second derivative is positive, then f attains a local minimum at A. Some people refer to f double prime A negative as concave down, and some people refer to f double prime A being positive as it being concave up. And if you ever hear people referring to inflection points, that's where the second derivative is equal to 0. Right? So if the derivative is 0 and it's concave down and it's a local max, and the second derivative is positive with the derivative 0, then it attains a local min at that point. And those are some of the basic properties that you probably even remember from single variable calculus on the differential side. The next theorem, whose proof can easily be constructed just from a special case of the mean value theorem, is a motivation for the existence of differential equations, and it says the following. Let's assume that f and g are both continuous functions on closed interval ab, and let's assume that f and g are both differentiable functions on open interval ab, such that f prime of x equals g prime of x for all x in the open interval ab. Then there exists a constant k in the set of real numbers, such that f of x equals g of x plus k for x in this closed interval ab. Some people will use c to represent your arbitrary constant. I'm just avoiding c to avoid confusion with the continuity class of functions. So let's do a couple basic examples that you definitely probably already know if you've already taken some differential equations courses. The first, let's assume that f prime of x is equal to x squared plus 5x plus 3. So if we want to use this theorem directly, all we need to do is just call this, for example, g prime of x. So the goal here is, who is g exactly? So using our properties of integrals and also derivatives, one should be able to see that this is going to be equal to f of x is equal to 1/3 x cubed plus 5/2 x squared plus 3x. And according to this, keep in mind, if f and g are continuous on AB and f of g is differentiable on AB, then there exists a constant k such that f of x equals g of x plus that constant k. Right? So some people refer to this entire object as the general solution to that differential equation, because here our unknown function is actually f, but technically we're looking at who the antiderivative of g prime is. In some sense they're equivalent, but we're trying to just invoke that theorem as directly as possible. So if this object is called an ordinary differential equation, then this object is usually referred to as the general solution to that differential equation. It's not a particular one because this is actually an infinitely sized class of functions whose derivative is just x squared plus 5x plus 3. But we can do a little bit better by instantiating what we call an initial condition. So let's assume that we have f prime of x is equal to x squared plus 5x plus 3, and let's assume that we require that f of 1 be equal to 2. Sometimes people refer to this as an initial condition, and some people refer to the coupling of these as an initial value problem. So an initial value problem, or an IVP for short. So, as we already know, the general solution to this differential equation would be equal to f of x is equal to 1/3 x cubed plus 5 halves x squared plus 3x plus some constant k. And we know that f of 1 must be equal to 2, so that means 2 must be equal to 1/3 plus 5 halves plus 3 plus k. So now we have an algebraic equation in k, and we should be able to solve for k. Take 2, subtract 1/3, subtract 5 halves, and subtract 3, and you should find that k is going to be equal to minus 23/6. Once you have your constant k, then we can state that f of x is equal to 1/3 x cubed plus 5 halves x squared plus 3x minus 23/6. And this is what some people refer to as the particular solution of the differential equation, or the particular solution of the initial value problem. And we'll get more into, is this particular solution a unique particular solution to this differential equation? We'll come back to that question at a later time. The next theorem combines the worlds of differentiability and Riemann integrability, and some people will refer to this as the fundamental theorem of calculus. So what we're going to do is we're going to assume three things. Let's assume that capital F is a continuous function on closed interval AB. Let's assume that little f is Riemann integrable in open interval AB. And let's assume that the derivative of capital F is equal to little f for all x in the closed interval AB. Then the Riemann integral from a to b of f, which some people will just simply write as integral ab of f, is actually equal to the difference in the boundary values of capital F, in particular f of b minus f of a. Okay, so that's actually very, very interesting. So since this theorem is actually so important, let's actually provide a formal proof for this, right? So we're going to assume that capital F is continuous, little f is Riemann integrable, and capital F prime equals little f. So let's start off with the Riemann integrability of little f. So let's assume that epsilon is greater than 0. So since f is Riemann integrable on open interval AB, that means there exists a delta greater than 0 such that if the norm of any partition is arbitrarily small, and we'll talk about what this norm is in just a moment, then the associated Riemann sum for that partition of f minus the integral from a to b of f, which we previously denoted as L, i.e. the limit of the Riemann sum, is going to be arbitrarily small. And the partition that I want to use is going to be the union from j is equal to 1 to n of closed interval on the left, xj minus 1, and then xj bracket, where that bracket is most of the time going to be a parenthesis unless we're on the rightmost subinterval of AB. Right, so b will be included in the last interval, parentheses otherwise. So this is what we have so far. So what do we need? So by the mean value theorem, and we're going to be focusing on capital F, because keep in mind we're assuming that capital F is continuous on AB. Therefore, the mean value theorem applies. Keep in mind, if it's continuous on the entire interval, it's continuous on every subinterval also, in particular in this partition, right? So if that is the case, keep in mind this is just A, B in disguise, then we have what? That means that there exists some number or numbers, let's call them uj, that belongs to the open intervals xj minus 1, xj, and here j ranges from 1 to n, such that capital F of xj minus capital F of xj minus 1 over xj minus 1 will be equal to the derivative. I'm just going to rearrange this because I want to take the summations of both sides. Actually, I don't mind writing a couple extra things. Why not? So this is going to be equal to capital F prime of uj. Right? So this is just the mean value theorem in disguise. So once I multiply both sides by this number, keep in mind these numbers cannot be equal to each other since the partition subintervals must be empty. What we're going to have is we're going to have f of xj minus f of xj minus 1 is going to be equal to f prime of uj times xj minus 1. And then I'm going to add up from j is equal to 1 to n both sides of this equation. So I'm going to do this for 1, 2, 3, 4, up to n, and then all of them up. So that's going to give us the sum from j is equal to 1 to n of f of xj minus f of xj minus 1. And that's going to be equal to the sum from j is equal to 1 to n of f prime of uj, and then xj minus xj minus 1. Keep in mind, capital F prime is equal to little f, so I can write that as little f of uj. And also note that this is just a telescoping series, which you should be able to show is just equal to capital F of b minus capital F of a. And the proof of that is actually not too difficult, because keep in mind, xj minus 1 forms the partition of ab. So once we have that, we're going to have f of b minus f of a is equal to the sum from j is equal to 1 to n of f of uj times the length of that associated subinterval, xj minus 1, and that is precisely just a Riemann sum for f. So if that is the case, what I'm going to do is I'm going to take the limit of both sides. So we're going to have the limit as the norm of the partition goes to 0 of SPF will be equal to the limit as the norm of the partition goes to 0 of f of b minus f of a. But the right-hand side is just a constant, so we don't really care about that because that's just going to be fb minus fa. But the left-hand side, because we already know that this is Riemann integral, converges to the Riemann integral of f on ab. So we have that the integral from ab of f is just going to be equal to f of b minus f of a, which is the result that we desired to show. The next theorem actually goes back to some of the applications we talked about in terms of optimization, and it goes to show how you can actually use derivatives to demonstrate that a function is monotonically increasing or monotonically decreasing on a point or on a set, or at a point or on a set. So let's assume that f is differentiable on some domain. Let's assume that a belongs to that domain. Then f is monotonically increasing on a if f prime of a is greater than or equal to 0 for all a in the domain. And we're going to say that this function is monotonically decreasing on a if f prime of a is less than or equal to 0 for all a in that domain. And we will add the word strictly monotonically increasing and strictly monotonically decreasing if we remove the equality sign on these inequality statements. So the proof of that actually comes directly from the definition of monotonically increasing and decreasing, and also from the definition of derivatives. So you should be able to see that quite easily. And also if, it actually comes from a few things, but I'll leave that exercise for you. So let's actually do a quick exercise, and let's actually go back to sequences because, sequences and functions do share an intimate connection with each other. So let's first off define this natural logarithm. I mean, most of you probably already know what the natural logarithm is, but let's actually introduce a formal definition for it. So this is going to be defined to be equal to the integral from 1 to n of 1 over t dt. So this is going to be an integral. Now, keep in mind, n is going to be assumed to be a natural number here, but t is going to be a continuous variable from 1 to little m. So the claim is that this sequence is a monotonically increasing sequence. Right? And that's actually very useful, especially if you plan to establish the convergence and or divergence of sequences. So let's see if we can prove this very useful thing. First off, let's assume that f is going to map 0 to infinity to the set of real numbers, and let's define f of x to be equal to the natural log of x, which by definition will be the integral from 1 to x of 1 over t dt. Right? So it's an integral defined function. So from the fundamental theorem of calculus, we can clearly see that f prime of x, which will be equal to the derivative of the natural log of x, will be equal to the derivative of the integral from 1 to x of 1 over t dt. So from the fundamental theorem of calculus, we know that that's just going to be equal to the function underneath that integral sign, provided that the lower bound is a constant and the upper bound is a variable. So once we see that, keep in mind that x belongs to 0 to infinity, so that means 1 over x is an always positive number for all x in 0 infinity. So if that is the case, that means the natural numbers, which are a subset of 0 infinity, also is going to be true. So we have that the derivative is always positive on the natural numbers, which means that this is a monotonically increasing sequence. And then we can go back to the definition of monotonically increasing sequences, at least what we had before, in particular that the natural log of m plus 1 will be strictly greater than the natural log of n, and that's going to be true for all natural numbers m. So you can use these identities, such as the fundamental theorem of calculus and derivatives, to prove properties of sequences. Because as long as the natural numbers are a subset of whatever domain you're working on, whatever's true on your interval will also be true for any subinterval that you have there. Now that we've talked about several applications of differentiability, whether it be to integrals, limits, differential equations, and several other matters, let's also introduce the concept of partial differentiability. So now what we're going to do is we're going to extend our domain to 2 or possibly more dimensions, but we'll keep it at 2 just for now. So let's assume that f maps the Cartesian product of AB to R with the point AB belonging to the Cartesian product A cross B. Then we say that f is x partially differentiable at the point AB if the limit as epsilon approaches 0 of f of a plus epsilon b minus f of ab divided by epsilon exists and belongs to the set of real numbers. Notice here that we're looking at this function being x partially differentiable, right? So we're focused on the first variable of this function. So we're looking at f of xy is equal to something with x and y in it. So we're looking at the first variable. Similarly speaking, we say that a function is y partially differentiable if the limit as epsilon approaches 0 of f of a b plus epsilon. So notice that we're focusing on the second element of its domain only, minus fab over epsilon, exists and also belongs to the set of real numbers. So let's also define the more general term. So if true for all a, b, in its two-dimensional domain, a cross b, we will write f belonging to dx, a cross b, for x partially differentiable functions, and we're also going to write f belonging to dy, axb, as the set of all y partially differentiable functions on a cross b. And we're also going to use the notation partial x of fxy. Some people also write this as dx of fxy to be equal to f of little x xy. So f little x is a new function. And similarly speaking, partial y of fxy. Some people also use this as dy of fxy will be equal to the new function f little y of xy. Right? So this introduces partial derivatives. So with partial derivatives now behind us, let's introduce our next theorem, which is actually fairly important with derivatives. So theorem number 12. And this function, or theorem, is due to Leibniz. And this theorem says the following. So suppose that f maps the Cartesian product of x with t to the set of real numbers, and let's assume that the point little x little t belongs to this two-dimensional domain. And also let's assume that f is x partially differentiable on this domain, and let's also assume that f is uniformly continuous in t on this domain xt, right? So when we say f is uniformly continuous in t on xt, that means we practically treat x as a constant and show that f is uniform on that function of t, right? So f is x partially differentiable in x, and f is uniformly continuous in t. Then, if that is true, and if one decides to do the derivative with respect to x, and keep in mind this is just a normal derivative of this function, right? So that should be f of xt dt, because keep in mind here, this definite integral, the integral from a to b of f of xt dt, since the variable of integration here is t, which is going to go from b to a, this t here goes away and you're just left with a function of x. So let's assume that we want to find the derivative of this function of x, but we aren't able to really evaluate the integral first. So what you can do is you can actually swap this integral and this derivative, and what you'll get here is the integral from a to b of the partial derivative with respect to x of this two-variable function fxt. So you can differentiate this partially with respect to x first, and then integrate, and you'll get the same function f prime of x, let's say. Right? So this is actually very, very useful. So let's actually do a nice little computation example of this to sort of show you how the Leibniz rule can actually work. So let's assume that somebody asks you, find the integral from 0 to 1 of x to the power of 5 minus 1 divided by the natural log of x dx. And let's call this integral star for now, because this is going to be our goal. So if you want to try this integral on your own blindly, feel free to do so. Else, let's see how we're going to do this. What we're going to do is we're going to begin by defining f of t. Notice that there's no t in this integral at all, but I'm going to introduce it. I'm going to call this the integral from 0 to 1 of x to the power of t minus 1 over the natural log of x dx. So this is a new function, an integral defined function, and it has the two important properties. The problem that we want, star, will be equal to f of 5. And also, if I plug in 0 for t, I'm going to have x to the power of 0, which is going to be equal to 1. 1 minus 1 is 0, and the integral of 0 is 0. So I'm going to have that star, our goal, is equal to f of 5, and also f of 0 is equal to 0. And I'll use that in just a moment. So I have this f of t. Now I'm going to find f prime of t. So that's the derivative of f with respect to t. So that's going to be equal to the derivative with respect to t of the integral from 0 to 1 of xt minus 1 over the natural log of x dx. Now, I want to use the Leibniz rule for limit swapping. And it's very important that you make sure that the assumptions on this function of x and t match. All right, so that's very important. And keep in mind, in terms of the theorem statement, my x and t have been swapped around, right? Because in the theorem statement, it was with respect to t. Here, it's with respect to x. So you need to make sure that this function, let's for example call this g, you need to make sure that g is partially differentiable in terms of t on your domain, which in this case is 0, 1 times r, for example, and g must also be uniformly continuous in the other variable x on this domain as well. So make sure to make those two checks. So once you can check them, you're going to have, this is going to be the integral from 0 to 1 of the partial derivative with respect to t of x of t minus 1 over the natural log of x dx. Keep in mind, partial derivatives with respect to t treat x's as constants, so you can write this as the integral from 0 to 1 because natural log of x is just a number as far as partial t is concerned, and I'm left with a partial with respect to t of x of t minus 1. So the derivative of 1 is just 0, and the derivative of x to the t is going to be equal to just a logarithmic derivative, because it's almost like the derivative with respect to t of 2 to the t, which we know is 2 to the t times the natural log of 2 from our fundamental rules. So once we perform that, we're going to have 0 to 1, 1 over the natural log of x, times x to the t times the natural log of x minus 0 dx. You can see my natural log of x's are going to cancel, and I'm just left with the integral of x to the t dx, which is just our basic power rule. So that's going to be x to the t plus 1 over t plus 1, and then we're going to send x to 1 as x goes to 0, and then subtract. So we're using our fundamental theorem of calculus here. So that means that f prime of t was equal to, so when x goes to 1, we're going to have 1 to the power of something, which is just 1 over t plus 1. And then when we plug in 0, we're going to have 0 to the power of t plus 1, which is 0, and 0 over anything is 0. So we have that f prime of t is equal to 1 over t plus 1. And then, well, that's just a differential equation f. So if that's the case, that means f of t must be equal to the antiderivative of 1 over t plus 1, which is going to be the natural log of t plus 1 plus some constant, let's call it k. So this is our general solution to our differential equation, but keep in mind we also knew that f of 0 was equal to 0, so this is technically an initial value problem. So that means that f of 0 will be equal to the natural log of 0 plus 1 plus k, and that's just 0. So we have f of 0 is equal to 0, which means that k is equal to 0. So that means what? So that means the particular solution to our differential equation is f of t is equal to 1 over t, or the natural log of t plus 1. Natural log of t plus 1. But why are we doing this? Keep in mind our integral from 0 to 1 of x to the 5 minus 1 over the natural log of x dx was the same as f of 5, right? And f of 5 is just going to be equal to the natural log of 5 plus 1, which is just the natural log of 6. That means the integral from 0 to 1 of x to the 5 minus 1 over the natural log of x is just the natural log of 6. And this method is actually very, very famous, and is sometimes called the Feynman's method for integration. So these are just some of the basics associated to differentiability and its connection to the other realms of mathematics, including but not limited to integration, differential equations, limits, and optimization. Hope you enjoyed this video, and I'll see you in the next one. Take care.